Hi, welcome you once again. Here we are looking into the disadvantage of a general method to find out the maximum flow in the given network. Here, when you are having less number of connections and less number of vertices, then we can use the generalized method to find out the maximum flow between the source and the destination vertices. But when you are having more number of vertices with more number of edges, then the updation of flow for each and every iteration is increasing more time complexity and also computational power. So to avoid that, we have to go for constructing the residual network for the given problem statement. And then for constructing the residual network, we can use Ford Fulkerson algorithm. So here the each and every edge is having residual capacity, which is represented C subscript R of the two vertices U and V equal to, here the capacity, given capacity, the edge weight between the two vertices U and V minus the flow between the those two vertices U and V. For example, here if you are passing the flow 1 in this path here, which is carrying 1 unit of flow between the source and vertices. So here when you are applying the flow 1 unit, then in the backward direction we will represent that flow between the vertices U and V, right? So here after applying this flow, then we have to calculate the residual capacity. Here the given capacity 3 minus the current flow is 1, so the remaining is here 2 units. So the residual capacity will be calculated for each and every edge after computation of the flow between source and destination for each iteration. For example, the flow is given 1 by using the path. That path is called here augmented path. S to A to B, B to C to D. Finally from the D we are reaching the destination T. So here the capacity, given capacity between this edges is represented here. S to A, this is 3 units, and A to B here 2 units, and B to C here 1 unit, and C to D here 2 units, and D to T here 2 units. So in this different capacity of these edges, the minimum edge weight is here 1 among this 5 edge weights. So this minimum capacity is called bottleneck capacity, because whatever flow we are carrying in these two paths, even though 2 units, this will allow only 1 unit. So the minimum capacity among this path edges is called bottleneck capacity. So here the residual capacity is mentioned here by using the arrow. The backward arrow is showing the flow here, how much we are having in this each and every edge. So based upon that, we are going to see the Ford Fulkerson algorithm for given graph G, which is having source and sink nodes S comma T respectively. Here we have to find out the maximum flow between the source and destination, which is depending on three important criteria. So one is the residual network. That means the residual network will have the flow and the remaining capacity of the edges in the corresponding given edges. And we have to construct the augmented paths for each and every iteration. And there is one of the theorem, max flow min cut theorem, which is dividing the vertices into two disjoint subset of the graphs. Okay, so here for example, the given graph is this one. The cut this red color line is saying the cut, so which is removing the two edges, the edge between the V2 to V4, which is also removed, and V1 to V3 is also removed. So that is the meaning of cut. So this cut is dividing the graph into two subset of graphs, you see, which is provide you from S2 V1 and V2. So this is one graph, right? And another subset is here V2 V3 to T, and V4 to T, and this one. So two graphs we are getting, different graphs. That's what we are saying. Two disjoint subsets we will get when we are applying the cut, which should have minimum value. The total of these edges which we are removing here, the v2 to v4 is having the 11, and v1 to v3 is having the 12. So 12 plus 11, the edge total cost is here 13 so 23, right? So this is the value which can carry by this particular graph, or I mean network. So right, so this will carry only the maximum flow is 23. So the capacity max flow is equivalent to the quantity which we are removing the edges. So this is called min cut. Okay, this is called min cut. That's what which is giving the max flow min cut theorem is characterizing the value of max flow with respect to the cut, which is dividing the network into two disjoint subsets. So here the Ford Fulkerson algorithm is used to finding the max flow, right, max flow of the graph by using residual capacity of each and every edge. After the calculating that max flow, then we can make the cuts by using the max flow min cut theorem. That min cut means the when you are cutting the edges, that means when you are removing the edges, it should give you two different graphs or networks. That removing edge weight should be minimum when you are making another cut in the graph. So here we will initialize the flow with 0 at initial stage. Then we have to check, is there any path available from the source to sink, that is called augmenting path. If that augmenting path is available, then we have to add that current augmenting path flow to the overall flow. Here overall flow as of now 0, then the flow which are finding here is calculated, that initial flow plus that current augmented flow. So right, so current augmentation flow. So we have to keep on do this until existing the path from the source to destination. So here the flow in the residual network is having the edge which are admitting the flow between the two vertices, and finally we have to identify the flow between the source and destination. Here our idea is to maximize the flow in the given network. The quantity of additional net flow from the vertex u to v, it should be checking before exceeding the capacity, right? That means here we are identifying the residual capacity between the two vertices using two calculations. One is in the forward direction. For example, in the forward direction CF of u comma v, the existing capacity. For example, here we are calculating the capacity in forward direction. The path here S to A to B, B to C, C to D, and here D to T, which is also carrying 1 unit of the flow. So here this augmenting path is allowing 1 unit of the flow. So this is the capacity we are calculating in the forward direction. So initially the capacity is 3, right, minus the flow is now augmenting path which is allowing flow now 1 unit. So 3 minus 1, so that is here 2. So like that, here already 2, so now we are allowing 2 units, then 2 minus 1 here, which is remaining capacity is here 1 in the forward direction. Like that, when you are taking this edge here already existing value is 2, then minus 1 unit we are passing in this iteration, then 2 minus 1 is here 1. So this is the residual capacity in forward direction. So like that, when you are calculating the capacity in the backward direction, here the 1 unit we have to allow. Now you see in the backward direction the 1 unit we are allowing in this path, right? So that's what which is mentioned here in the each and every edge between these vertices. So here the capacity between the v comma u, right? So here we are adding, initially this was 0, so in this backward direction here every edge is having 0 units. So now 0 plus the flow between the u comma v. For example, when you are taking this path, the flow between each u and v here 1 unit, so 0 plus 1 is 1. So this is the value here we got the value 1. Like that, here now we are calculating the value in this d to t. So here initially in the backward direction we had 0 units, that's why we didn't mention the backward edge, because the value is 0. Then 0 plus the flow between the d and t is here 1 unit, so 0 plus 1 is 1. So that's what which is represented here. So we have to calculate the residual capacity between each and every vertices using the forward direction and backward direction. Based on this concept, here we are representing the flow network with collection of vertices and edges. Here we are having the source and destination s comma t. Here the residual network of the network has to be calculated for given graph by using the flow, which is represented by using the f. Then if you are using the f dash as a flow, that means for each and every iteration we will calculate the f dash, right, for the first iteration, then f2 dash for the second iteration, f3 dash for the third iteration, like that. So here initially we are making the flow is as a 0, then we have to keep on add this. So f equal to, right, so here f equal to, then f plus f dash, right, then f equal to f plus f2 dash. So like that we have to keep on calculate in the same direction. So that's what we are mentioning here. In the same direction we are adding, in the different directions it will be cancelled. That means if it is the backward direction, here we are subtracting that. So 3 minus 1, that is the value we are representing here, flow value. That's what we are saying in the name of cancelled. Then here we have to identify the augmenting path for each and every iteration in the name of the flow from the source and destination. For example, here we are using the 4 vertices. Here the 2 is the capacity which is allowing, here 3 is the capacity which is allowing, here 1 unit is the capacity. So here the minimum capacity among these 3 edges is 1 unit. So this is the bottleneck capacity allowing in this flow between the source and destination. So that's what which is given as a formula. In the forwarding path we have to identify minimum value among this u and v. So in this u and v 2 units, in this u and v 3 units, in this u and v 1 unit. So minimum of 2 comma 3 comma 1 we have to identify in this path p. That's what which is given here. So minimum of 2 comma 3 comma 1 is the value. So based upon this we have to identify the maximum quantity of net flow between the source and destination by adding augmenting paths for each and every iterations for the given graph. Thanks for watching. We will see the example in next video.